The problem asks, what volume of gas will there be for 3.6 grams of CO2 at 10 degrees Celsius at sea level? What volume will 3.6 grams of CO2 occupy at 10 degrees Celsius at sea level? And we're given the R value is, the gas constant, is equal to 0.0821 liters atmospheres over mole Kelvin. Well, to answer a problem like this, I think you need to first ask yourself, which formula should you use? You know it's about a gas, and so some options are the combined gas law, which begins P1V1 over N1T1, and continues to say equals P2V2 over N2T2. Or we know the ideal gas law, PV equals nRT. And we know Dalton's law of partial pressures, where we have our P total with our partial pressures of gas A plus gas B, and so on. And we want to think which one of those would we want to use. Then you'll want to assign your variables. Say what pressure is equal to, what volume is equal to, etc. If there are any values that need to be converted, this would be the time to do it after that. Get them into their correct units. Your temperature, no matter which formula you use, has to have the units of Kelvin. If you're using PV equals nRT and you're using this given gas law, well, you better make sure your pressure is in atmospheres, your volumes in liters, your N is in moles. And of course, the temperature is always in Kelvin. The last thing that you would do is solving, plugging in values and solving. Now, I've given two options for this to my students. One would be to first rearrange the letters, the variables, then plug in your numbers and solve. Option two, you just go ahead and plug in your numbers, do your algebra and solve. For me, it depends. I like to rearrange the letters sometimes, especially when I'm doing, say, PV equals nRT. That's an easy one to rearrange for whatever variable I'm trying to solve. Sometimes when I'm using the combined gas law, I find that it's easier to plug in the numbers and then solve. You use whatever works for you. So let's take a look at the original problem again. What volume will 3.6 grams of carbon dioxide occupy at 10 degrees Celsius at sea level? Well, we have one gas, we have one set of conditions. So we're going to use PV equals nRT. Step 2, we're going to assign our variables. We're told that we're at sea level, so the pressure must be 1 atmosphere. We don't know our volume, that was what the question asked for. It told us we had 3.6 grams. To know N, we will have to convert our grams into moles. From the periodic table, we need to find the molar mass of carbon dioxide, CO2. We know that one carbon has a molar mass of 12 grams per mole, and two oxygen atoms we would multiply by 16 grams per mole each. They add up to 44.01 grams for 1 mole of carbon dioxide molecules. There's an invisible 1 whenever you go per and then a unit. So, when we take 3.6 divided by 44.01, the answer comes out to be 0.082 moles for our number of moles of CO2 when we have 3.6 grams of carbon dioxide. Again, our equation's PV equals nRT. You could plug your values in and solve if you want to do that. Volume is originally being multiplied by pressure, so you need to divide both sides. The opposite of multiplying is dividing. Divide both sides by pressure, and then plug in 0.082 for your number of moles. That's what we got up here. 0.0821 is the gas constant. Just a coincidence. I made up all these numbers. Didn't mean to have them be the same number. 283 Kelvin is what our 10 degrees Celsius would be equal to. Sorry, I didn't show that. Oh, there it is. At your temperature, you add 273 to anything that's in degrees Celsius. Then we're going to divide that by 1 atmosphere for our pressure. And when you do all the math, you get the volume is equal to 1.9 liters. Option 2, into PV equals nRT, 1 for your pressure times your volume is equal to 0.082 moles times 0.0821 for your gas constant times 283 Kelvin. Either way, you get 1.9 liters. So your volume here shown with all the units canceling out is going to be in liters because that's the only unit left after you've multiplied and divided by everything else. The volume of 3.6 grams of CO2 at 10 degrees Celsius at sea level is 1.9 liters.